Today I'm going to teach a particular lab which is taught in BSCH 191 or 291, and the name of the course is Chemistry Lab 1, and the name of the practical is determination of chloride ion in a given water sample by Argentometric titration, and we are going to use potassium chromate as an indicator. So the name of the method is Argentometric titration, and the objective is to find total soluble chlorides in a given water sample, and potassium chromate would be the indicator in our case. The name of that salt is potassium chromate. Okay, this is a very simple titration. You can call it a colorimetric titration because the color change would be observed. Also, you can call it a precipitation titration because during the titration, precipitation happens. Why it is important? It is important to determine the amount of chloride ion, to know the amount of chloride ion, because this is the most found form of soluble salts which could be responsible for the hardness of the water. If I say sodium chloride, potassium chloride, magnesium chloride, calcium chloride, so these are many salts, even ferric chloride. So these are many salts which are found in water sample in chloride ions. And all these are somewhat responsible for the direct or indirect effect on our body, even on plant body. And we know that particularly these two are responsible for the hardness, as we know that hard water is a water where you have soluble calcium and magnesium salts. So these salts are soluble in water. So that is why these particular two salts are responsible for hardness, and all other things as direct or indirect benefits, and sometimes we outside a certain limit they are even harmful. So we need to know that whatever water we are using for drinking or any other purpose, or washing purpose or any other purpose, it is very important to know the amount of chloride ion present in that. Even I can give you certain example like more than 250 or 300 ppm. ppm stands for parts per million. ppm stands for parts per million. So if I have more than that amount of chloride ion in a given water sample, then the taste is not good for that water. So obviously that water cannot be a good suitable water for drinking. So that is why we need to know these things, and why we are calling it Argentometric titration. Simple. By we are going to use silver nitrate here for doing the titration. And as we know that silver nitrate is a secondary standard. Hope everybody knows what is secondary standard. Who does not know, for them I am saying that secondary standards are those which has to be standardized by a primary standard. That means itself you cannot prepare a certain concentration solution of secondary standard. Yes, you can prepare that, but the concentration may change after some times. The solute which you have dissolved in water sample, that can reaction with air, that can be oxidized with air, or sometimes that can be oxidized or reduced under the sunlight. So for all these reasons, these solutions may change its concentration with time. So that is why whenever we need a particular concentration silver nitrate solution, first we have to make it, then we have to standardize it by the help of another primary standard solution. Now in that case, we are going to use sodium chloride. Yes, so this will be the reaction for standardization of this will be the reaction that AgCl will be precipitate, and along with that NaNO3 is forms. Now in that case, again we are going to use K2CrO4 as an indicator. Now what's the point? Point is, when you are using K2CrO4 indicator, that means silver nitrate can do again a parallel reaction with K2CrO4. Which reaction? In that reaction, it will produce Ag2CrO4, which is also form a precipitate, but this will be a red precipitate. Along with that, we will have potassium nitrate. So the point is, in a conical, I have taken that silver nitrate which has to be standardized. Then I have added K2CrO4. So obviously, this will be the first reaction. What I can expect, that means you will observe a red precipitate in your conical. Then when you are adding the standard NaCl solution, remember I told you that's a primary standard solution. That means whose concentration is known to me and which cannot be changed with time or when it is kept for a time. So the concentration of NaCl is known. When I am adding NaCl from the burette, the red precipitate will be changed to silver chloride. So that's the science behind the standardization of silver nitrate. And if I know this, by the help of this famous equation, I can calculate the normality or even molarity of the silver nitrate solution. That's how we can standardize silver nitrate solution. Now coming to, if I know the concentration of silver nitrate, how can I know the amount of chloride present in our water sample? So in our water sample, we are going to take, again I am taking a conical, and inside a conical I am taking again 10 ml of water sample. You can also take 10 or 25, no problem. 10 or 25 ml of water sample you can take, and here also I am taking potassium chromate as an indicator. Remember, potassium chromate gives you a very yellow color soluble salts. So obviously when you add potassium chromate, the whole solution becomes yellow but transparent. So that's not a yellow precipitate. I am talking about yellow soluble salts. That means the whole solution becomes transparent. So when I am adding water sample and K2CrO4, which I have to use approx 1 ml. So the whole solution becomes yellow but transparent. Then I am starting drop by drop. Then I am starting drop by drop. What? That is silver nitrate solution from the above, which has to be standardized before starting that experiment. So that's the standardization part, in which I have already standardized silver nitrate solution, and here I am adding silver nitrate solution to find that how much chloride ion is present in the water sample. So obviously the same reactions will happen. That means I am talking about again two parallel reactions, and these parallel reactions are silver nitrate can react to both. First, you will observe that silver nitrate may react with potassium chromate, where you will observe a red precipitate, and parallelly another reaction can be expected, that is silver nitrate reacts with NaCl to form AgCl, which forms a white precipitate. That was a red PPT, and that is a white PPT. So both the reactions are possible, but as we have in our water sample a lot of chloride ion, so obviously the amount of chloride ion is more initially. So all the reactions will happen through silver chloride. That means the above reactions will come backward, and all reaction will go to that direction. That means initially maybe you will able to observe a little bit of red precipitate by local titration, but when you are shaking and mixing the whole conical solution, then you will able to observe all the precipitate which are coming is basically a white precipitate, because the amount of chloride ion is more initially. So as we proceed in titration, the amount of chloride ions will decrease. So in that case, when you have almost similar chromate ion and chloride ion, then you will be able to observe that a little bit of red precipitate will start coming. But still the whole solution is not enough red. So at the end of the titration, when all the chloride ion will be finished, that means all the chloride ion will react to by that reaction. Then after that, one extra drop of silver nitrate will make that red precipitate, and now this time the whole solution becomes red, and you will clearly able to observe that the red precipitate comes and it will persist. So then that's the time when you have to stop your titration, and that's the end point. So that's what you have to remember. What is that? At end point, red precipitate starts coming and it stays. That's most important, because previously also we have observed the red precipitate started coming, but when you check the whole solution, that was vanished. But this time the red precipitate came and it persists. That's most important. So that's how you have to record the volume, that how much volume you have added, how much volume of silver nitrate you have added, and you will use this to determine the strength of the silver nitrate, strength of the chloride ion, not silver nitrate. Silver nitrate is already known to me because that's a secondary standard, has been already standardized by another primary standard. So that's how we can calculate the amount of chloride ion. Let me talk about the calculation also. The calculation says that that's a very calculations remains the basic knowledge. That means the gram equivalent of chloride equal to the gram equivalent of silver nitrate. That means I can say that gram equivalent of silver nitrate is equivalent to gram equivalent of chlorine. Yes, we are considering Cl minus, but the mass of one electron we are neglecting. So Cl minus and Cl both has the same mass. That's what I am considering. Which means that 1000 ml 1 normal silver nitrate is chemically equivalent to 35.5 gram of chlorine, which is the equivalent mass of chlorine. That is why I have written 35.5. And similarly, in the period reading, that means how much volume of silver nitrate I have taken. You can also take 3 or 4 or 5 data and take the average of that. Let's say that average is coming the VML. So let's say that average of that period reading of silver nitrate volume is VML, and the concentration of silver nitrate, what we have already determined by the standardization by another primary standard, let's say that is Y normal. So if that two things are already determined before starting that calculation, then VML and Y normal silver nitrate must be equivalent to this. Now this is the amount of chlorine which is present in our taken volume for titration. That means, let's say we have taken 10 ml of water sample. Let's say we are doing the titration by taking 10 ml of tap water or any water. You can also take 25 ml because we have already done it with 10 ml or 25 ml. No problem. Whatever you have taken, write it here. So 10 ml of tap water, let's say it contains this, then 1000 ml of water contains this. So that is the concentration, what we can say in gram per liter. 1000 ml means 1 liter. So that is gram per liter. Which means that also you can convert it if I multiply it with 1000, that becomes milligram per liter. And milligram per liter means this is also known as parts per million. So that is a very nice and a very easy calculation to determine the chloride ion in a given water sample. 2-3 things you have to remember, because in that process can be only possible when you are maintaining a pH of 7 to 8 in water sample. Because at higher pH, silver nitrate can form silver hydroxide. And at lower pH, at very acidic pH, K2CrO4 forms K2Cr2O7. That's a redox reaction. Everybody knows about this. Cr2O4, that's chromate, it will convert it to Cr2O7. Okay, look at the oxidation number. The oxidation number of Cr2O4 in chromium will be, it will be +6, and here it will be again +6, because 2x minus 14 equal to -2, which means that x equals to 12 by 2, that is +6. And here also 2x minus 8 equal to -2, that is x equals to . So how can I do this? That should be, 1 second. That should be CrO4. So here also it will be +6. So if I want to balance that, I need 2 H2O here. So I need 2 H plus here, and along with that 2 electron. So that redox reaction happens in acidic pH. So these are the precaution you have to take when you are doing this practical. Okay, that's all. Thank you.